So lots of people here run Hetzner or know of Hetzner. How many of you run Kubevirt? Anyone interested in Kubevirt? Sorry? Okay, cool. So definitely some interest for Kubevirt. So I'll share my experience building metal clusters in Hetzner to run Kubevirt. And a bit of context, I work for Bunnyshell. It's a SaaS and platform company focusing on building ephemeral environments for dev teams. So for example, teams of say 10 developers or the more developers, the better. They kind of get a bottleneck of environments available to test their works. And we automate creating environments for each pull request. We create an ephemeral environment, it's deployed to Kubernetes, but it kind of abstracts the Kubernetes part away from the team. And when the PR is closed, the environment is closed as well. And why did we build this project specifically with Hetzner in mind? Traditionally, the environments are based on containers. All the services run in containers, and we allow the users to do remote development, as in they actually connect or open a terminal in the pods and run their, node, run, watch, whatever tools and pipelines, whatever servers they want, they can use, they can run over there. And it synchronizes the code from their local laptop to the code in the pod, and they're able to basically run their local environments in the cloud. But user feedback was that they would actually, a lot of them would prefer the actual VM experience as opposed to the container experience, because in container, it's immutable, it's difficult to install, some of them are distroless, it's difficult to debug, whatever. So we set out to provide a way for them to run VMs. Since we were already running the environments on Kubernetes, then Kubevirt was the obvious way to go. And one particularity of running VMs is that they're mostly idle, especially development VMs. They're mostly idle. So CPU is idle, but the memory is not. So memory is still allocated. And this is why we had to optimize for RAM per dollar. And this led us to Hetzner, which you are all familiar with. EU-based, offers both VMs and metal servers, and it's very cost-effective. A comparison here of various cloud providers. So, of course, you already knew this. It's running VMs in Hetzner, it's about 25% of the cost of running them in other cloud providers. So, obviously, this is what set us on the path to use Hetzner, but looking deeper, we looked at their VM versus their metal offerings. And I don't know if you know, VM pricing, probably no, scales linearly. So you pay more, you get more RAM in like a proportional ratio. But metal scales way better. So a 3-node metal cluster, you can get 1.5 terabytes of RAM, 192 vCPUs, and it will cost less than 600 euros a month. And for comparison, yeah, in AWS, it would cost you roughly 10 times that. Of course, you have to manage it. And that's the fun part, right? Yeah. So the architecture we chose is a hybrid cluster. We wanted, in order to be as cost-effective as possible, to use a high availability control plane built on VMs, because they don't need that much RAM and CPU, and are, let's say, easier to manage for a control plane. And any number of worker nodes running on metal servers. Both nodes, all nodes would be Talos. We would have a load balancer for the control plane. We would use vSwitch, which is the networking infrastructure of Hetzner, to connect the metal servers. And as a stack, Talos, Cilium for CNI, Longhorn for CSI, Kubevirt, of course, and we would deploy with KLUCTL, and I'll return to it a bit later. Anyone here know of KLUCTL? Just one person, cool. It's a really cool project, and I'll explain why later. So we faced quite a number of challenges related to networking between VMs and metal servers, installing Talos on Hetzner specifically in VMs, then in metal servers, consistent naming of the metal servers, storing the configuration somewhere, cluster storage, of course, and an overall slow feedback loop for GitOps, and we'll go into each of these challenges next. First of all, networking. The problem is that by default, the metal servers provided by Hetzner are not connected to the cloud servers by in Hetzner. So the solution is to create a network, which is like a VPC, with dedicated subnets for metal and virtual servers, then connect the metal servers to a vSwitch, which the vSwitch, by the way, is tagged VLAN solution, and expose the cloud subnet to the vSwitch. And then if we achieve this, then the virtual and the metal servers can communicate at layer 2. Then challenge number 2 was installing Talos on Hetzner VMs. So VMs in Hetzner don't have an option to start to boot Talos. So we have to get the Talos image out there. Has anyone done this? Okay, so you pretty much, I guess, suspect how this is going. We use a project called HCloud Upload Image that installs Talos on an image, creates a snapshot of the VM, and that snapshot can then later be used as the base image for new VMs. Challenge number 3, installing Talos on the metal servers. This was slightly more complicated because the particularities of Hetzner, for each metal server you buy, or rent from them really, they just provide the public access, public IP address and SSH access to a server running in rescue mode. And you are responsible for installing Linux on that system using the rescue system. And bringing up the private IP, private networking via VLAN tagging requires Linux to be running. So we couldn't use Omni. So we had to do this manually, basically installing Talos over public internet. And this is one problem. The other one was that the disks in metal servers in Hetzner, for some kind of reason, especially in Talos, tend to switch their names or have their names randomly assigned when they boot. And sometimes when the server would reboot, it would boot from the other from the other drive, and it would be basically bricked. And then another challenge is that servers that you buy from auction in Hetzner are not identical. They have different number of drives, or even different names for drives, and the drives come in different sizes. So the solution, a lot of custom scripts. For installing, the approach is to SSH into the VM, into the server, the physical server, curl, download the image, the Talos image, and DD copy to disk with DD. But at the same time, we collect information we discover information about the disks during this installation and save it in a central repository. And you can see here in the right-hand side, one such piece of information. So for example, for a server with IP address 1234, we would store the primary disk ID and the secondary disk. And this would be used later when we render the Talos configuration dedicated for that specific server. So each physical server needs to have its custom Talos config. And we store this config in Git without any secrets. So yeah, that's challenge number 3. Now, consistent node naming. The problem here is that we might add or remove physical nodes to the cluster. Each node is identified basically by its public IP address, and we need to assign it a private IP address. We need to make a static private address, and we need to make sure that there are no conflicts. So, for example, if we remove server number 7 and add server number 8, the static address needs to be different. And for this, pretty simple solution, we store a cluster node index file and we commit it to Git. And this is an example of that file. So it's just a list of server IPs, basically. But we would have to make sure that we manually maintain this whenever we add new servers to the cluster. And for example, the command that installs Talos on one metal server, you see below here, uses the I for index number 3. So this would install Talos on server number 3. Challenge number 5, config store. We need a way to store all this configuration in a way, of course, that's suitable for a team. And we decided for each cluster, we would create a dedicated Git repo where all the config files go. No secrets in there, but shared for the team. And this is for an example of one of the basic config files for each cluster. You can see the Talos version, the schematic ID, a name, endpoint, host name, whatever. Networking IP ranges. And a very important line 19, the VLAN tag. So that's the VLAN tag used to connect the physical nodes to the vSwitch in Hetzner. Challenge number 6, storage. As you pretty much all know, Talos, when it installs, it uses the whole disk, so you can't install it to just a partition. So it would pretty much waste big disks. So we ended up using Longhorn, because Longhorn is able to use the free disk space on the physical disk used by Talos. And also it can use the other disks as well. So it uses, it's a file system storage solution versus a disk-based. So it solves this problem without waste. Number 7, slow feedback for GitOps. So once we got the cluster infrastructure up and running and we started managing Kubernetes manifest and installing Kubernetes deployments, whatever, initially we used Argo or Flux. But we had to go to the commit, push, deploy feedback loop, which is kind of slow. Like any typo would mean 10 minutes for it to deploy, see it doesn't work, and retry again. So this is why we ended up using KLUCTL, which I told you about earlier. It's cool because it allows manually deploying from local files, so without going to the GitOps, the whole GitOps process, but it also supports GitOps. So initially we do all the trial and error with the local files, and then when we're ready, then we switch to GitOps. Okay, we're good on time. Steps to build a cluster. Because of the mixed hybrid nature of the cluster, we had to really plan this well. So once the prerequisites were taken care of, we could install Talos on metal servers, but not deploy the configuration on those servers. Then we would prepare the Talos config files. We would create a control plane on VMs. Then we would apply the configuration to the metal servers, because the configuration for metal servers requires that the control plane is up and running. And then we would create the ingress load balancer, and we set up the Kubernetes manifest. Let's go into a bit of details for each step. So prerequisites were buying the servers, of course. we would need to make sure that they have SSH key access. We'd create the vSwitch, add the metal servers to the vSwitch. Then we would create the VPC in Hetzner. We would create subnets for the virtual server, subnets for the physical servers, and connect the two. And at this point, we have metal servers and just a way for metal and cloud servers to communicate at layer 2. Installing Talos on metal servers required for initially we would bootstrap the cluster configuration. We have a set of scripts that create a template of configuration files. Then we need to edit the IP addresses of the physical servers in that configuration and the Talos schematic. And then we can go start each metal server in recovery mode, as I said, and the installed script would connect to SSH and write the image to the disk. So at this point, metal servers are running Talos, but have no Talos config. And we have stored information about each server in our config store in this file, config discovery /IP address. Next, preparing Talos config files. So once we have that information extracted from each node, each physical node, we are able to build its Talos configuration. And we have a pretty complex script that uses lots of templating and environment substitution to generate the configuration for each physical node. Once we have this, we can create the control plane. The control plane, all control plane nodes have similar configuration. And we create 3 of them. We create a load balancer in front of them, add them to the load balancer, create DNS records if needed. And at this point, we bootstrap the cluster and have a cluster with 3 worker nodes and no worker nodes. Then, at this point, we're able to apply the Talos configuration to the metal servers because the control plane is up and running. And once we do this, we're able to create the ingress controller load balancer, install the ingress controller, add the metal nodes, of course, to the load balancer, and then we're pretty much able to do Kubernetes. From here on, we have a Kubernetes cluster up and running. Next would be installing the CNI. We use Cilium. Installing ingress controller, I mentioned already. CSI Longhorn required a particular step to add each physical server disk to Longhorn for it to use. By default, Longhorn only uses the free space on the Talos root disk. So we have to particularize each server. Longhorn on each server basically needs to know about all the images and all the disks and their capacity. And this is the loop that we run through with the KLUCTL. And once we're happy with the results after many iterations, we switch to GitOps. And this is the proof that we actually did this. You can see 6 nodes on this cluster. 3 of them have 64 CPUs and half a terabyte RAM each, and the other 3 are small control plane nodes hosted on VMs. And that's it. Thank you. You will be able to find the scripts, all the scripts here in this repository. We're opening it up next week. And thank you. That's it.